In these videos, we're going to take a look at the various ways to be able to solve systems of differential equations. And the goal is to be able to get two equations of an independent variable, likely t, to which we could substitute those back in. It'll simultaneously satisfy both of these differential equations that comprise the system. So let's take a look at the various methods, and most of them are going to be very similar to the methods we use to be able to solve regular systems. So we have this x prime equals negative 3x plus 2y, y prime equals negative 3x plus 4y, and then both the initial conditions at 0 are equal to 1. One of the ways that we learned how to solve a system of equations all the way back in algebra was by substitution. And that works pretty well for this example, right? And very similar to regular systems of differential equations, or I'm sorry, regular systems of equations, excuse me, it's often a trial and error sort of thing. So maybe try substitution first or try elimination. It just depends on what the equation looks like, right? So let's take the first equation and let's solve it for y. Right? So if we solve that for y, we're going to add 3x divided by 2. So we're going to get 1/2 x prime plus 3/2 x is going to be equal to y. We can substitute that immediately into the second equation. We also need y prime. Y prime is going to be 1/2 x double prime plus 3/2 x prime. And we can substitute that back into the second equation as well. And now we'll have an equation solely in terms of x. By substitution, we can say the second equation becomes 1/2 x double prime plus 3/2 x prime is going to be equal to negative 3x plus 4 times 1/2 x double prime plus 3/2 x prime. And now we just have an equation that's in terms of we have an equation, and excuse me, this is just going to be x prime, and this is not going to be, so this is just 1/2 x prime. So I was looking at the second as the derivative instead of just the y, and then this is just going to be x. So sorry about that. So now we just have an equation in terms of one variable, and it's going to be a second order differential, but that's not too bad. We can go ahead and collect like terms and distribute. So notice that we're going to have 6x and negative 3x. So that's just going to turn into a positive 3x. 4 times 1/2 is 2x prime. And then we have this 1/2 x double prime plus 3/2 x prime. We can multiply through by 2, clearing out the denominators. So x double prime plus 3x prime equals 6x, excuse me, plus 4x prime. And then finally we can set this equal to 0 and get a really nice, easy, homogeneous differential. X double prime minus x prime minus 6x equals 0. The auxiliary equation, m squared minus m minus 6 equals 0. So we go all the way back to where we solve homogeneous second order differentials. We get our auxiliary equation, we factor that auxiliary equation into m minus 3, m plus 2 equals 0. And so finally we get our two roots, m1 is 3, m2 is negative 2. And we end up with at least a general solution for x at t. So x at t is going to be equal to, and by the way, this is a case 1, if you remember they're distinct roots, c1 e to the 3t plus c2 e to the minus 2t. And we're going to hold on to this because this is our general solution. All right, so just hold on to that. We do have to find what the particular solution is eventually, but for right now I think we're good. All right. And now what we can do is we can go ahead and find that particular solution by substituting x at 0 is equal to 1. Or we could just wait and we could do them simultaneously, which might be better since the equations are dependent both upon x and y. So let's figure out what y is now. Notice that y can be found by back substitution. So 1/2 x prime plus 3/2 x is y. So let's just kind of remember that. 1/2 x prime plus 3 halves x is equal to y. So we do need x prime at t. And so the derivative is going to be 3c1 e to the 3t by chain rule minus 2c2 e to the minus 2t by chain rule. And we're going to substitute x prime, and we're going to substitute x, and then we're going to be able to solve for y and get a general solution. So y at t is going to be equal to 1/2 of 3c1 e to the 3t minus 2c2 e to the minus 2t plus 3 halves of the original x, which was c1 e to the 3t plus c2 e to the minus 2t. All right. Now we can clean this up really nicely. Notice that we have 3 halves by distribution, c1 e to the 3t, and another 3 halves. So that's just going to turn into 6 halves, or 3c1 e to the 3t. Notice that we have -1 after we distribute the c2, and then we have 3 halves, c2 e to the minus 2t. So 3 halves minus 1 is going to be 1/2. So this will be 1/2 c1 e to the minus 2t. So now we have the general solutions to both. So now we have our x at t, which is our c1 e to the 3t plus c2 e to the minus 2t, and then yt, 3c1 e to the 3t plus 1/2 c1 e to the 2t. And remember that we had the initial condition that y at 0, which was equal to x at 0, was equal to 1. They were all equal to 1. So now we can make our system. And we're going to substitute 0 back in for t. Now notice when we substitute 0 in for t, all of the e to the 3t's and the e to the 2t's are just going to become 1. And so here's our system. We're going to have, by substituting 0 in to these two, c1 plus c2 is 1. And then for the other one, we have 3c1 plus 1/2 c2 is equal to 1. We can multiply the first equation by -3 to eliminate. So we would have -3c1 minus 3c2 equals -3, and then 3c1 plus 1/2 c2 is equal to 1. And then we can just add the systems together. All right. This is going to turn into -5 halves c2 equals -2, and then we end up with c2 is going to be 4/5. Right? So that's really nice. c1 is going to be equal to, so notice that c1 is equal to 1 minus c2, just solving that equation. So c1 is going to be 1 minus 4/5, or 1/5. Finally, we back substitute back into y and x. So remember that x at t was equal to c1, which is 1/5 e to the 3t, plus c2, which is 4/5 e to the minus 2t. Right? So that works out really nicely for x at t. And then for y at t, now be careful with this one. Remember, for y at t, it was 3c1. All right, so it's going to be 3 times a fifth, or 3/5 e to the 3t. And then it was, for y at t, 1/2 times 4/5, or 2/5. So that's going to be plus 2/5 e to the minus 2t. All right. We could go through if we really wanted to, and we could go ahead and take the derivatives, substitute those back into the original differentials, and see if they work. All right. Or we could just believe that this is indeed the system, or the solution to the system. All right. So that's one method that we can use, is substitution. Now, in the subsequent videos, we're going to take a look at different sorts of ways to be able to solve these differential systems.